In chapter 22, you learn the concept about the electric field, which means that the charge, no matter if it's positive charge or negative charge, it will generate something called the electric field, which will uh, into the space, which means that the charge is here, but the field can be go to uh, the other places. Actually, can go to infinite far away. So actually, you can calculate the E field generated by some sort of continuous charge using the integration. Actually, the integration is difficult to calculate by hand calculation. So the scientists maybe 200 years ago try to find some other method to really calculate it more easily. One one important tools is to use the Gauss law. Of course, nowadays you can just use the computer using the numerical method to calculate the integration. It will be very trivial, as you should have learned the Riemann sum, which is the same as the integration. So actually, Gauss law is a tool to calculate some sort of geometric. So actually, this is the overview for the electromagnetism. Actually, in this semester you learn of them, and actually in this chapter you learn the Gauss law, and also another form of Gauss law is the magnetic version of the Gauss law. Of course, in this textbook, D will seldomly appear, but this is just captured from the internet. But actually, you know that what I really want to show here is that for the Maxwell equation, there are four. Actually, you don't really need to drop it. Actually, for the Maxwell equation, there are four importance law. Two of them called Gauss law. One is for electric field, another one is for magnetic field. And the Faraday's law and the Ampere's law. You'll learn Faraday's law in chapter 30, and Ampere's law you'll learn it in chapter 29 and also chapter 32 to make it complete. For the version in chapter 29, it will be up to here. In chapter 32, I will also explain what is this term, which is called the displacement current. And this is the integral form, and in the textbook you will mainly see the integration form, but I will also try to let you know the point form or the differential form, because using this we can derive some interesting formula. We can solve some PDE, solve some PDE, and then you see how does the electromagnetic waves come from. So I just let you know from a top view what we'll learn in the coming future. So in this chapter we'll learn this one. So actually, we introduce a concept called the electric flux. Actually, in the last chapter, for the I already forgot what is it called. As we can visually express, the E field. So for positive charge, we can draw the electric field line. Electric field lines. Suppose we have positive charge, we can have electric field line onto different direction. And if this charge is positive, the electric field line will point outwards. If the charge is negative, then the electric field line will point inwards. It doesn't really matter we have 6 lines or 8 lines or But if we have two different putting together, then the density of the line really means something. For this one, which means that this charge is larger, this one is smaller, and this one is further smaller. This one smaller than these two. So in this case, we try to draw a circle, try to draw a circle, try to draw a circle, try to draw a circle for these three cases. So actually, we can count that there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 intersect points between the electric field lines with this circle. So we have the number 8, and all the lines are pointing outwards. So this is plus 8. Okay, keep this in mind. So this is plus 8. Okay, and then we can count it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, we have plus 16. Also pointing outwards, so it is plus. So for this one, 1, 2, 3, 4, and pointing inwards, so that it is minus 4. So actually, this number is has the same ratio between this plus Q, plus 2Q, negative 5Q. What I mean is that we should have we'll have 8, 16, negative 4, and that one is Q, it should be something like Q plus 2Q, negative 0.5Q. So these two ratios is the same. So the point here is that we can try to count the number of arrows intersect with the imaginary circle. This is imaginary. It does not really exist. We just imagine there is a circle there, and we try to count the intersect point between the circle and the electric field line. Then we find that the ratio between the number of intersect points and the charges is the same. So we try to further go deeper. We try to go deeper into this concept, which is the electric flux. We define it in a physical way, in a physics point of view. So we have the area vector dA, which means this is a vector, so it has a direction and the magnitude. So the magnitude of the area vector is the area itself, which is a scalar or a number. So the magnitude of the area vector is the area itself, and the direction of the area is the direction perpendicular to the surface. So it is a plane. It will be very easy to define. It's just something perpendicular to it. For example, if it is the right board, the direction perpendicular to it should be pointing outward or pointing inwards. Both are okay, but actually you need to define by yourself. For an open plane, you can define this side or that side. Both are okay, but actually it needs to be perpendicular to it. If it is a curvature plane, then you need some calculus. You need to take the if it is a curvature. If it is a curvature plane, I don't know how to draw a curvature plane. So you really need to cut it into very small element, and then you can regard as very small area to be a flat plane, so that you can define the direction perpendicular to it. So this concept is a bit difficult, but let's imagine this is very small. So this is maybe a perfect square or a perfect rectangle. So you can define the direction perpendicular to it. Okay, so now we have talked about the area vector, and the next is the electric flux. The electric flux goes through this area, can be written like this. D phi is the E inner product with the area vector, or you can write it as delta phi. Delta phi is also very small changes, or in the calculus, we usually write it as d something, dx, dy, d phi, something like that. So the inner product means this is two vector inner product. So you multiply the magnitude of them, and then you multiply the cosine theta. The theta is the angle between this is dA, this is dA vector, and this is E. So theta is this angle. So for the inner product, we calculate the inner product by multiplying the magnitude of both of the vector, and then multiply the cosine theta. The theta is the angle between them. So we have the flux, which means that if E has the same direction, or at least not the other side. If it is this side, then d phi should be positive. If E point to the right side, or maybe with an actual angle, then d phi will be positive. If E is perpendicular to the area vector, then cosine theta is 0. Which means that d phi is 0. If E is pointing to that side, so cosine theta is between 90 degree and 180 degree, then cosine theta is negative. So d phi will be negative. So this can sufficiently explain this idea. So if the E field pointing to the outwards, it will be positive. If it is pointing inwards, it will be negative. So here for closed surface, we will always define positive to be outwards and negative to be inwards. Remember this important idea. So here tells you that an E field vector pierces a small square patch on a flat surface. Only the x component actually pierces. So here in this case, this area is on the YZ plane. So the dA is on the x-axis, is on the positive x-axis. So the only the x component of the actual pierce of the patches, the y component skim through across it. So you can imagine E cosine theta is the x component of the E field. So the area of the patch is perpendicular to the patch with a magnitude equals to the patch area. So I just explain that. So just now we have the infinite small infinite small electric flux here, d phi. So we have d phi. So therefore, for a large area, something like this, So we need to integrate the d phi over the area. We need to integrate the d phi over the area. So it is a integration, actually a surface integral. So actually, it looks horrible, but actually, it is not. Well, for single variable calculus, you know that if you have f of x dx, if you integrate it from a to b, it is something like you have f of x here, and then x equals b, and then this integration, this definite integral, is the area under f of x, if f of x is larger than 0. If it is smaller than 0, then maybe something like this. Then if you have AB, so that you will have the integration will be something like this area plus this area minus this area. Okay. So this is a integration for the single variable case. If now we have a curvature f of xy, so on the xy plane, so that if we integrate f of x, y with respect to dx, dy, and x is from a to b, y is from c to d, y is from c to d, so that you integrate this a, b, wow, very hard to draw. Very hard to draw. Don't know how to draw. So maybe like this. C, D. So it will be the volume under this curve between z equals to axis, z equals to 0 plane, and then x equals to a, x equals to b, y equals to z, y equals to d, between those plane, and then this is the volume. So this is the area. So this is the area under f of x, and this one is y equals to 0, x equals to b, x equals to a. So for this one, it will be between f of x, z equals to 0. So this is the upper and lower, and you will have x equals to a, x equals to b. Between these two planes, and also between y equals to z, y equals to d. So this is the double integral. So now the case becomes even more complicated. Now suppose you have a charge, Q, you generate E field. Maybe you define a closed surface. Closed surface mean 封闭，就是它没有洞的意思。With no holes, so it is a closed surface. I cannot draw a closed surface. Maybe you can imagine it is a sphere. So on this sphere, you can really calculate all the d phi equals to E dot dA. E dot dA. So for this point, for this area, we have the E pointing to this side, so that DE and DA can be calculated. For this point, you can also calculate E dot dA, but they may be different. But they may be. So actually, you can calculate all the flux regarding to different small area, and then you just integrate them together so that it will become a integral looking like this. And if it is a closed surface, we'll draw a circle here. If this is a closed surface. If it is just a plane, maybe just a plane, put it here, and then we try to calculate the electric flux go through this plane. Then you can only you should only write like this. That this is a flux for this case. If it is a closed surface, we'll draw a circle here to mean that it is a closed surface integral. So actually, this is called the total flux, and this is called the net flux. Because the net flux means if it is positive, which means that the flux is going outside. Maybe there is something going inside, something going outside, but on average, the overall flux is going outside if the net flux is positive, and the vice versa if it is negative, which means that the net flux is going inside. If it is zero, which means that the flux is on average stable, not going outside or going inside. So here we summarize that. If phi is larger than 0, then the flux is going outwards. If phi is negative, we call the flux is going inward. So any questions up till now? Okay. Well, I suppose I have explained this one. So yeah. So let's see a sample problem. How could we use it? So a Gaussian surface. We usually call a closed surface a Gaussian surface. Have we mentioned? Maybe we will mention it later on. But if a surface is closed, we will call it a Gaussian surface in the form of a cylinder, 圆柱体 cylinder of radius r, immersed in a uniform electric field. With the cylinder axis parallel to the field, what is the flux phi of the electric field through this closed surface? Yeah. So for 3D, of course, you can use the Cartesian coordinate, which has a XYZ plane. Maybe you'll be familiar with it, a bit more easy to consider. But in calculus, you will learn two other coordinates rather than the Cartesian coordinate. Cartesian coordinate， 就是皮卡的坐标，就是 coordinate 是直角坐标。So in calculus, you also learn the cylindrical cylindrical coordinate and also the spherical spherical coordinate. So this is called the 圆柱坐标。这个 spherical coordinate we call it 球坐标。So for cylindrical coordinate, it will be something like this. We have z direction, but for the xy plane, we have r and theta. We have r and theta. And for the spherical coordinate, we will have something like this. We will have r, and then we will have theta. Theta. This is theta, and this is phi. So we will use r, theta, and phi to represent a point. Here we'll use r, theta, and z to represent a point, because if it is cylindrical, so r, theta, and z can be separate, so that it will be easier to express a point. For spherical, if we use r, theta, and phi, so that we can fix r and then we can rotate to any other angle. For this one, of course, we use xyz. So for the cylindrical coordinate, is something like you have a polar coordinate, 极坐标 coordinate at the z-axis to it, then it is a cylindrical coordinate. So here we have a cylindrical here, and what is the flux? Also, if you're going through the closed surface. So for the left side, we call this one small a, and then for the side, we call it b. And for the right side, we call it c. So now the E field is pointing to the right side. So here phi equals the closed surface integral E dot dA. So which will be nothing but integral of E dot dA of the A part plus the B part E dot dA, and plus C part E dot dA. So for the whole surface is the whole cylinder. So we can separate into three parts: part A, part B, and part C. So just add them together. So actually the E field is pointing to the right side. So for EA, E is pointing to this side, A is pointing to that side, and E is a constant across this area. So this one is nothing but negative EA. And for this one, dA should be pointing to the outer. You can imagine for the cylindrical, the area vector should point to this side for this point, and for this point you're pointing to the upward. For that point you're pointing to the downward. So it's always the radial direction. So as the E is pointing to the right side, so they are always perpendicular to each other, which means that cosine theta is 0. Cosine theta is 0 means that the inner product between the E and dA should always be 0. So this term is 0. And for the C part, it should be plus EA, because E and A should be points to the same direction, and E is uniform across the whole area. And so it's nothing but E times A, because you integrate a constant. It's just very easy. It's just something like you can imagine. You can imagine for single variable integration, if you just integrate 3 dx from 1 to 5, it will be nothing but 3 times 5 minus 1, right? So it's just this one minus this one is the length, because it's something like you have a rectangle. You have a rectangle. This one is 3, y equals 3, y equals 0, and then x equals to 1, x equals to 5, 1, 5. So this side is 4, this one is 3. So you integrate a constant is nothing but this one multiply the length. So it's nothing but 12. So for this case, if you integrate the E dot A should be a constant. So if you integrate for the whole area, it's nothing but E times the total area E. Any questions? So next one. So now we consider a uniform electric field given by this expression plus the Gaussian cube as shown in the figure. What is the electric flux through the right faces, left face and top face? And we'll calculate the two later. And so let's calculate the flux, electric flux through the right face first. So actually, for the right face, the area vector should point to the positive x-axis. So E dot dA should only consider the x component. Maybe you should familiar with the inner product with the unit vector. So we have the unit vector of x-axis to be I hat, j hat to be the unit vector on the y-axis, and k to be the unit vector on z-axis, so that we have I dot I to be 1, j dot j to be 1, k dot k also to be 1. And if we have I dot j, which will be equals to j dot I, will be 0. If we have I dot k, which will be equals to k dot I, will be also be 0. And if we have j dot k, which will be equals to k dot j, which will be 0. So in some of the advanced physics textbook, you use a simple notation to express all this one. You use delta ij to really express it. As long as I equals to j, then it will be 1. I equals to j equals to, then it will be equal to 1. If I is not equal to j, then it will be 0. It will be 0. So this notation means 1 if I is equal to j, 0 I is not equal to j. But so if you know this one, then for example, if you have a vector A, which is something like 3i plus 4j, and then if you have a vector A like this, and if you have a B, would be maybe 5j plus 6k. Yeah. So you can calculate it like this, the inner product A dot B like this. So it's something like you calculate the multiplication 3i plus 4j dot 5j plus 6k. So you can distribute 3i, 5j. So we have 3i, maybe 3 times I, and multiplied by I dot j. And then we distribute 3i, 6k. So we have 3 times 6 multiplied by I dot k. And then we plus 4j, 5j. So we have 4 times 5 j dot j. And then 4j, 6k. 4 times 6 j dot k. Actually, you know that this term are all 0, and this one is 1. So finally, it will be 20. It will be 20. So if you know how to use the unit vector to calculate the inner product and outer product or cross product later on, then it'll be quite convenient. And actually, some of the assignment I intentionally choose. Some of the assignment will use this kind of calculation. So for this case, the right face, on the right face, yeah. So here, dA is on the x-axis. So we only consider the x component of the E field, which means that phi r is integrating r, and then E is 3x. E dot A is nothing but 3x dot 3x dA. So we always tackle the inner product part, and then we drop out the 4j. So now, actually, this one x is equal to 3. So here x is equal to 3. So we have 9 dA for the right surface. And actually, the area of dA is of the right surface is 2 times 2, which is 4. So actually, it is 9 times 4, which is 36. And the SI unit should be nm squared over c. nm squared over c. Yeah, here. This is the SI unit. Both of them should be the same, but this is the SI unit. So So maybe we can quickly finish the other two. So for the left surface, dA point to the left side, dA point to the left side. So actually, so phi left should be integrating the left, and then 3x. 3x is the positive x-axis, and dA should be negative x-axis. So we will have minus 3x dl. And in this case, x is equals to 1, x equals to 1. So we have minus integration of the left surface, and then we have 3 times 1 dA. And a is 4 also, so it is minus 12 nm squared over z. So this is the second one. For the third one, which is the top face, which means that dA points to the positive y-axis. So here we only consider the y component, y component of the E. So the top surface phi t is integrating the t E dot dA. E is 4, and dA is on the positive y-axis. So we have 4 dA. So finally, we have 4 times 4, which is 16 nm squared over c. So for this one.